we've introduced the Internet Protocol, and we know it operates at the network layer, IP. It's a core part of the Internet. All of your devices that attach to the Internet must implement IP. Your mobile phone, inside the operating system, there's some software that implements IP. In your laptop, in your desktop PC, there's some software that implements IP. You need the Internet Protocol to be able to send data to other devices across the Internet. So it's the core part. You don't need all of the other protocols, but you must have IP. We're going to first today look at how the protocol works, and we'll see it's quite simple. Compared to some other protocols, it's quite simple. And then at the end, we'll come back to IP addresses and see this return to the structure of IP addresses, those 32-bit addresses, and see how they're used. We spoke about the IP datagram. With IP, we have hosts and routers, or computers. Your laptop as a source computer wants to send to some destination computer on the other side of the world. It sends via routers. The routers are datagram packet switches. So you send to the first router, that router would send to the next router, and eventually it reaches the destination computer. What do you send? You send an IP datagram. This shows the structure of the IP datagram. In particular, it shows in the header, so we have a header plus data. In the header, there are some values that have certain meaning. For example, the first 4 bits of the header indicate the version of the protocol being used. The next 4 bits of the header indicate the length of the header. We need that because the header length may be variable. If we have options, it's not 20 bytes, but it may be 24 bytes, 32 bytes. So we specify how long it is in this field. And then some other fields, some we haven't gone through or we will not go through, like diffserv, ECN, the flags and fragment offset. They're used for special features. We just cover the basics of IP in this course. We have a source address and a destination address. The source, both addresses are IP addresses which are 32 bits long. So we have the row here graphically corresponds to 32 bits. And the source address is the address of the computer that creates the datagram, so the original source. The destination address is the address of the final destination. If I'm sending from my laptop to the Facebook web server, the source would be that of my laptop and the destination of the Facebook web server, and I send via routers. So the source, even though it goes via a set of routers, the source and destination remain the same. Always the original source, the final destination. And we have the data, which may be variable sized. How do I send the datagram via a set of routers? That's what we want to cover. IP is a connectionless internetworking protocol. It's used for internetworking. Connectionless means we do not set up a connection. Some protocols do set up a connection, IP does not. Setting up a connection involves, from the source to destination, sending maybe some special message saying, I want to send some data to you, and maybe the destination responding saying, OK. That can be useful for preparing the destination to receive the data, preparing the buffer space, different variables that it's going to use, different features. But we know when we looked at virtual circuit packet switching and circuit switching, if we set up a connection, it takes time. Time before we send the real data. So there's some overhead of setting up a connection. IP does not use that. IP is connectionless. We just, when we have data, we send it as packets or datagrams. So datagram packet switching concept. It's simple. So it's easy to implement. There's few overheads of setting up a connection. So it's few overheads, simple, flexible. It can work for many different types of networks or applications. So IP is connectionless, no connection. in an internet, when we use IP, we distinguish between two types of devices, hosts and routers. Let's draw an example internet. Where I'm going to draw the hosts as squares, and a host is our end user station, a laptop, a phone, a PC, a printer. And our router is our datagram packet switch. It's the thing that forwards the datagrams to the destination. In this picture, I'm drawing the subnets as clouds. So far we have one host attached to this subnet and also a router attached to the same subnet. Maybe there are more hosts on that subnet. Just an example internet where we have several hosts, the squares, and several routers. And in this case, let's give them names. This is subnet A, B, C, D, E, and F. 6 subnets in this internet. And on some of the subnets there are hosts attached, and there are, here we have 3 routers connecting those subnets together. The hosts are end user devices, things that you and I use to create the data and receive the data. Routers are the datagram packet switches, the devices that forward the data through the network from source to destination. What's the difference between them? How many interfaces does my laptop have? We've asked this question before. How many interfaces, network interfaces, do you think my laptop has? How many different types of networks do you think I could connect to with my laptop? What are they? 2 or 3? Name them. Wireless LAN, Bluetooth, and plug the cable in wired LAN or Ethernet. Okay, so my laptop has 3 network interfaces: wireless LAN, Bluetooth, and wired LAN or Ethernet. Normally, how many do I use at the same time? 2. 2 in unusual situations, but most times I would think 1. Okay, I'm connected to the SIT wireless LAN, accessing the internet. If I plug the cable in, the wired LAN, then my computer would automatically start using the wired LAN and stop using the wireless LAN. Normally, on your end user device, you use 1 interface at a time. You can use multiple. It's a bit more complex, and sometimes you need to set up the operating system or some software to do it for you. But normally your end user device, your hosts, even though they may have multiple interfaces, normally use 1 at a time. That's why I've drawn them here with just one, let's say one cable attached to each host. So usually use 1 interface at a time. Routers normally have 2 or more interfaces, because the role of a router is to connect subnets together. This router connects subnets A, B, and C together. You can imagine that this router has 3 cables plugged into it. 1 going onto subnet C, 1 to B, and 1 to A. And it may be receiving data and transmitting data on those interfaces at the same time. On each of the cables, it may be transmitting and receiving at the same time. So that's one practical difference. Normally your host has 1 connection to the internet, to a subnet. Routers normally connect subnets together, so they have multiple connections. The core difference between a host and a router is that A router forwards datagrams. A host does not forward datagrams. And as a result, a host is either a source or destination. A source creates the datagram when we have data to send. A destination is the recipient of that data, the one that receives it. Routers normally just forward it on to someone else. So if this is our source, it creates some data it wants to send to someone, so that someone is here, our destination. Then what we may do is create a datagram, the source, send it to a router, the router send to another router, and then onto this destination. The process of the routers sending on, so they receive and then send, is called forwarding. Okay? We forward it on to someone else. So routers forward datagrams. A host never will forward a datagram. If for some reason the datagram goes to here, and it's not the destination, that would be an error. This one will not send it to here. By definition, a host will not forward a datagram. Only a router will. Okay? Hosts are either a source or destination. A router forwards datagrams. In some cases, in practical cases, routers may also be sources and destinations. For example, if I wanted to configure this router to manage it somehow, then I could send a datagram to it as the destination and it would respond. So routers in practice may be sources and destinations. Hosts always are either a source or a destination. A router can forward datagrams. A host never forwards datagrams. And that's how we distinguish between a device we call a host and one we call a router. Other than that, they could be any computing device. A router could be my laptop. I can configure my laptop as a router. It's not hard. In practice, in large networks, routers are usually dedicated hardware. So it's not my laptop, it's a dedicated piece of hardware which has many ports to plug cables in and is built to forward datagrams fast. So we have two types of devices in our internet, hosts and routers. Of course, we also have devices inside these clouds. So I haven't shown them here, but inside the cloud, maybe some Wi-Fi access point, some switch, some modem. We have devices inside the cloud, but from IP's perspective, it ignores them. It doesn't care what happens inside here, so long as if the source can send a datagram, it can be delivered to anyone on that subnet. If we can, so that what happens inside here should be able to deliver a datagram to here or to the router. So from IP's perspective, we hide the details of what happens inside the subnets. Whether it's wireless LAN, Bluetooth, ADSL, wired LAN, any technology, IP hides those details. It should work no matter what the technology is used inside the cloud. We've said this before, we distinguish between routing and forwarding. Routing is the process of discovering the best path or paths. Forwarding is the process of sending the datagram across one of those paths. And we do that in the internet, where in our internet we'd have some way to discover what are the best paths from this source to each destination. And similar from the other sources to all the destinations. We'd discover the best paths. That discovery would be the role of a routing protocol, an IP routing protocol. Once those best paths are discovered, then where do we store that information? Where do we store the information about the best paths? In a routing. Where do we store information about routes or paths? Where do we store information about routes? Where? What's the name of the thing that we store the information? Not a packet. When I find I've found the best path from source to destination is via this router and this router, so I know the path, and then I store some information about that in a routing table. Remember, a routing table is simply, or in the simplest view, is some table that says to reach some destination, the next node is this router. So we have a routing protocol that discovers the paths and then stores information about the paths in a routing table. So it populates the routing table with data. And then we use the internet protocol to perform forwarding. Forwarding is quite simple. When we have a datagram, if we know the destination, we look up the routing table. We find the destination, we find the next node in the path to send it to, and we simply send it to the next node. That next node also has a routing table. The destination is over there, it looks up the routing table and realises it needs to send to this router. And we keep going until it's forwarded to the destination host. So we distinguish between the phases of discovering the paths, IP routing. Then when we discover the paths, we store information in routing tables. When we want to send data, we simply use those routing tables to forward the datagrams across the network. So separate tasks of routing and forwarding. Both of them, well, routing creates the table, forwarding uses the table. Let's go through an example in a bit more detail. I'm going to put some values in some routing tables. D means destination, N means next. So let's say that I've discovered the best paths through the network. I've already determined what they are, and I put some data in the routing tables. This is the routing table for the source. First, we need to give some names. What can we call them? Let's call this one A1. It's on subnet A. It's a device on subnet A. This one's A1. Let's call this A2. This E1, E2, F1, F2. So we give some identifier or address to the hosts, and this is just a conceptual address. We'll see later we use the 32-bit IP addresses in this to replace these. And let's also give addresses to routers. And we'll give it an address to each interface of the router. This router here has 3 interfaces. One's connected to subnet A, one to C, and one to B. Let's give them each a name or an identifier. Let's call this one A3. So we'll have A1, A2, A3 on subnet A. And this interface, let's call it B1, C1, and do also for the other routers. So this router is connected to C, D, and F. Let's give them numbers, C2, D1, F3. F3 because I already have F1 and F2. When we give addresses, we should make sure those addresses are unique. You shouldn't have 2 devices with the same address because it will not uniquely identify it. The values I used are just for an example. They could be different. D2, B2, E3. They are the addresses of our devices. In fact, some devices have multiple addresses, in particular routers. I'm going to put some data in the routing tables to create a path from A1, and let's make our destination F1. And let's say the best path was to this router, and then up to this one, and then here, and then to F1. All right, it's more hops, but let's say it's much cheaper to send across this path than to send across here. So the best path from A1 to F1 is via A3, then to B2, then to D1, and then on to F1. So a routing protocol would be used to discover that information and then put information about that path in the routing tables. So from A1's perspective, to reach the destination F1, what's the next node? The next address? A3. Okay. From A1, if the path is going to be this path, to go to F1, the next node or the next address is A3. And from A3's perspective, here's the routing table. To reach F1, what's the next node? We're going to try this path just to make it more interesting. Okay. Well, we look at the next router, B2. Okay. So from this router's perspective, to reach F1, assuming we're taking this longer path, then we'd send to B2. And for B2, this router, if we're sending to F1, we'd send to D1. D2 is in fact, is an address of the same router. Routers can have multiple addresses. So we normally say the address of the next router. This device, to reach F1, we would send, if we're here, we send to F1 direct. Instead of writing F1, I would write, say, direct. Direct, in this case, I mean, it's on the same subnet. We don't need to send it to another router. We've reached the network where that destination is, so we can send direct to the destination. That's a conceptual view of the routing tables. There will be other entries for other paths, but that's the one we need for our example. Before we go through the steps, we're going to go through on some slides and this on the board. Any questions about what I've drawn here? It may not be clear to some people. We've got hosts as squares, routers as the circles. I've given addresses to each interface. And the way that I gave addresses is that all the devices on one subnet have the same letter. Subnet A is A3, A2, A1, but unique number. Okay, 1, 2, 3. We cannot have 1, 1, and 1. They would not be unique addresses. And on a different subnet, again, the same letter, B, B, and a unique number. We'll see when we come to real IP addresses, the same structure is used, except real IP addresses are longer, 32 bits. What this slide shows is that the protocol stack for some of those devices. Here we have 3 routers in between our source host and destination host. So similar to the path we have on the board. So imagine this source host is A1, this is A3, B2, this router is D1, and this is host F1 for the example. And we're communicating between the source and destination host, let's say using HTTP, an application protocol, and using TCP as the transport protocol. Importantly, both the hosts and the routers all implement and use IP. Okay. The hosts also have some application and transport protocols, HTTP, TCP. The routers don't care about the application and transport protocol. They only care that we're using IP. And another thing we see in this protocol stack is that over each subnet, so the subnet A, which the host and the first router are connected to, we must use the same data link layer and physical layer. For example, we use wireless LAN. So from this, if we're using wireless LAN, Wi-Fi, then both this router must support wireless LAN, as must this host and this host. We all use the same technology. Maybe across this next network we're using something else, ADSL. And in this network we're using wired Ethernet. And here we're using something else, Bluetooth. So in each of the subnets, the LAN or wide area network technology may be different. That is, we use different data link and physical layers. That is between here and here. All the devices on the one subnet must use the same technology, but on different subnets you can use different technologies. So technology B, technology A, general C and Z. But they all use the Internet protocol. Note that the routers need to support both technologies. This router on this interface supports wireless LAN, and on this other interface ADSL. So a router may support multiple technologies and use them at once. Any questions before we proceed? We're going to show a datagram going through this network. What we're going to do is, in fact, is the steps I'm going to describe are shown on this slide. This slide shows for each computer the steps that are taken inside IP. So up the top is the transport protocol, down the bottom is data link layer. Here are the steps taken inside IP, or a summary of the steps. I'm going to describe them as we go through. You can match them back to there. So that is a zoom in of, for example, what happens here, and the same as what happens here. Source computer wants to send to the destination computer. It creates a datagram. That is, the application generates data, and eventually IP application generates data, passes that data to IP, and IP realizes I have some data I need to send to someone. Let's create an IP datagram. Has a header, some data. In the header there are different fields, version and other fields. The ones that we care about just for this example, what's the source address? The source computer is A1. In the real datagram it's a 32-bit IP address. Instead of using real IP addresses in this example, let's just use these letters and numbers, because it's hard to write down 32 bits all the time. Let's say it's A1, but really that represents a 32-bit IP address. The destination, F1. And then maybe there are other fields as well. But let's focus on the source and destination. The source of this datagram is A1, and it's going to the final destination of F1. Once it creates the datagram, if you see on the flow chart, it checks, am I the destination? So this is what A1 is doing. Is A1 the destination? Anyone? No. A1 is not the destination. So in that case, it looks up its routing table. A1 looks in its routing table. The destination is F1. It looks in the routing table. Okay, there's an entry in the routing table that says if the destination is F1, send to A3. So now the source computer uses that routing information and sends that via the data link layer to A3 on our network. It would send to here. How does it send to here? Using our wireless LAN technology. Okay. So that's the first step. A3 receives that datagram. When you receive a datagram, you check, am I the destination? Is A3 the destination? No, the destination is F1. Then I check, so since I'm not the destination and I'm a router, I look up my routing table and see who the destination, or how to reach the destination. We now look in the routing table. The destination is F1. We need to send to B2. So now it simply sends using the data link layer to B2. The source and destination is not changed along the way. The source is the original source and the final destination. We send to B2. B2 checks, am I the destination? No. Look in the routing table to reach F1, the destination, send to D1. D1 checks, am I the destination? No. Look in the routing table, send direct. That is, use our technology, Bluetooth here, to send to the device with address F1. F1 receives, checks, am I the destination? Yes, I am the destination. Simple. Remove the header, take the data, and send the data up to the high layers. And then we've received the data. And now you know how the internet works, because that's the core of IP, of the internet protocol. It's one of the simpler protocols you'll come across. There's no acknowledgement that comes back. There's no timeout and retransmit like we've seen in ARQ schemes. There's no flow control. There's no set up a connection. Simply send the datagrams via this forwarding procedure. Send to the next node based upon the routing table until it reaches the destination. When it reaches the destination, remove the header and process the data by sending it up to the higher layer. Any questions about that procedure? It's captured in more detail in 2 slides forward, but that's the basics. That's all you need to know. Any questions?
No.
Good. You'll be getting 100% in the exam if there's no questions.
Why that's from B going to D1? Why there's no routing table?
There's a routing table up here. It's just a small one. All the hosts and routers have routing tables. I haven't drawn them for all the hosts, but they do have routing tables. Some may be more complex than others, but in theory, all of them have a routing table. And the internet protocol, we just use the data in the routing tables to determine who to send it to next, and until it reaches the destination. How are the routing tables created? Who put the data in these routing tables? Well, there are separate routing protocols that do that for us. IP itself doesn't do it. There are other routing protocols, some acronyms that represent real ones: RIP, OSPF, BGP. These are routing protocols that find the best path and put the data inside the routing table. We're not going to go through how they work. You'll maybe get that in computer network architectures and protocols next semester. But all we know that we find the best path and store the next node in the path in the routing table. How we do that, the details are left for those individual protocols. So routing is not built into IP itself, it's left to other protocols. IP simply uses the routing table, uses the information in the routing table to forward datagrams. Now, in our real internet, we don't have 6 or 7 subnets, we have hundreds of thousands of subnets, billions of nodes, billions of hosts, hundreds of thousands of routers. If we want to create our routing tables in a large network, the tables can become very large and become unmanageable, in fact. So there are some ways to simplify the routing tables. We'll go through them. Makes routing easier and makes management of the routing tables easier. It makes it possible to route in a large network, such as the real internet. So let's go through these 3 ways to simplify the routing tables. First way, we already know. You don't store the entire path in the routing table, you store just the next node in the path. A1 in its routing table did not store A1, A3, B2, D1, F1. That was the path. We only store the next node in the path. We only need that. And then it's the next node responsible to getting to the subsequent node and so on. So we only store the next node in the path. We don't store the entire path. That's all we mean by storing next hop routes. What about, let's consider what do I store for the route from A1 to F2, okay? A1 to F2, what do I store? What about from this router to F2? It could be C2 or B2. Most likely it's B2 because if to reach F1 is via B2, a host on the same subnet most likely to reach F2 would also be via that path to B2. What if on this subnet F we don't have just 2, we have 200 different hosts, F1 up to F200? Then what we do is in the routing table we'd have F1, F2, F3 up to F200. But we can simplify that. Instead of storing routes to individual hosts, let's say instead of storing the 200 different entries, let's do this. To reach anyone on subnet F, send to A3. Doesn't matter if it's F1, F2, F200, F10,000. Anyone on this subnet, send to A3. And same here. Anyone on subnet F, send to B2. Typically, we do not store routes to destination hosts. We store routes to destination subnets. And how that works is that A1 wants to send to F1, looks up. Okay, we know by the address F1 must be on subnet F by our definition. So we send to A3, send to B2, this would send to D1, and this one knows the destination is F1 and then can send direct to F1. If the destination in the IP datagram was F2, it would send to F2. So it's only up to the last router in the path to deliver to the individual host. The other routers just deliver to the router attached to that subnet. Okay? So store not routes to individual hosts, but routes to subnets. That makes our routing table much simpler. If there are 10,000 hosts in a subnet, we just need one entry, not 10,000 entries. And it makes updating those routing tables easier. Okay? So that's network-specific routing. We route to networks, not the hosts. And it's up to the last router to deliver to the host on that network or subnet. So that simplifies routing and routing table management, especially when you have hundreds of thousands of routers and millions of hosts. The last simplification is, what if A1 wants to send to someone on network E? Next node on subnet E, A1. What if he wants to send on subnet C? Subnet D, A3. If there were 100,000 more subnets there, we'd always send to A3. We only have one option, okay? So instead of storing all of these values, let's do even simpler. Have a default route. Star here means any value. It's like some pattern matching, a wildcard. If the destination matches any value, send to A3. Then A3 would determine to send it in the appropriate direction. This is what we'd call a default route. If we don't have a path, then use this. Always send to A3. So this sort of wildcard concept can be used to match multiple values. This is just some general notation, the star. In practice, it's implemented differently, but the concept is we don't have to match a specific subnet, we can match a range of subnets. And again, this is my laptop on the internet where there are hundreds of thousands of subnets, millions of hosts. I need just one entry in my routing table. That is, what is the next router that my laptop's attached to, the default route. So it simplifies routing tables. We can do it also on routers. Any questions on how we can simplify the routing tables? Don't store entire paths, just store next hops. Don't store paths to hosts, store paths to subnets. And where possible, you have a default route, that is one that matches any other value. The common way to read these routing tables is row by row. That is, you check, does the destination match the first row? If not, try the second row. If not, the third row. And then at the last row, we'd normally have a default route, and that would tell us where to send the datagram. You'll see some more examples of that in your homework. Let's finish on IP then, and return to IP addresses. We know how we forward datagrams through an internet, some ways to manage the routing tables. That's the details of the forwarding steps, but we went through that. That is, create a datagram, is the destination my address? If not, use my routing table and send to the next node. So this just describes formally what I described when we sent the datagram through our example internet. Fragmentation and reassembly is a special feature. If we have data which is too large, we can break it into smaller fragments and reassemble at the receiver. You can read through that in your own time. We will not cover how that works. Datagram of a lifetime, we've mentioned as well, this one. It's the time to live field in the header. The source sets the TTL to be some value in the header. Every router decreases the value from 3 to 2 to 1. If it gets to 0, this one will not send anymore. It's only used in special cases. For example, if there's an error in the network. Normally it's set to large values like 64 or 255. So normally it's not an issue. It's just a way to limit the number of times it's been sent in the network, the datagram sent in the network. And that brings us back to IP addressing. We had a couple of examples on it yesterday. Let's return to how IP addressing works. Look at our example network. I've given addresses to our hosts and routers. I've also given addresses to our subnets. I said we have subnet A. Think of A as an address. Host A1. A1 is an address. A router has multiple addresses. I've used letters and numbers. In the internet, we use our 32-bit IP addresses. Note the structure. The address of hosts and routers have two parts, the letter and the number. The letter identifies the subnet and the number identifies the computer or device in that subnet. A is the subnet A. 1, 2, 3 is the separate computers in that subnet. We do the same with IP addresses. We have a 32-bit IP address. Some bits identify the subnet. The remaining bits identify the device in that subnet. What else do we have? Each subnet has different addresses. In our internet, we cannot have subnet B and subnet B. They must be unique subnet addresses. Inside a subnet, the computer address must be unique, 1, 2, and 3. And we'll see we can have some special addresses as well. So an IP address from yesterday's lecture. IP address is 32 bits in length, 32-bit binary value. It has two parts or two portions. First n bits is what we call the network portion. It identifies the subnet, like the letter in our example. The remaining bits identify the device, like the number in our example. And the first bits are called the network portion and the last bit's called the host portion. The host identifies the device, the network, the subnet. Same as our example. All subnets in the internet have unique network portion. We have unique letters in this simple example. In the internet, the network portion must be unique in each different subnet. All devices in a subnet have the same network portion, A, but unique host portions, 1, 2, and 3. The question is, if we have 32 bits, some bits represent the network, some the host. Which bits? We split somewhere down the middle. Well, not the middle, but we split somewhere of those 32 bits. The way to split has changed over time. In the past, they used what was called classful addressing or subnet addressing. Nowadays, mainly classless addressing. And that's what we're going to describe, classless addressing. Why do we split between network and host portion? So we can have these manageable routing tables. So we can specify to send to network F, not to F1, F2, F3, but to an entire network. Let's look at how we determine the split. What's the IP address in dotted decimal notation? Quickly calculate. So yesterday we covered dotted decimal. calculate yourself. I'll check the answer. Anyone have an answer? You can use your calculator, that's okay. You can use your phone for a calculator. Convert that 32-bit value into a dotted decimal notation. You split the 32 bits into chunks of 8 bits each, and then convert that 8-bit binary value into a decimal value. What's the answer? You can use your computer, that's okay.
Convert to what?
Dotted decimal notation. 192. 228. 17. Last one. 57. Let's check. Sounds good. Make sure you know how to do that conversion. Okay? Split it into 4 8-bit numbers. Convert each 8-bit number into a decimal number. 192, 228, 17, 57. Separate by dots. The human-friendly form, the real value, the binary value. That's easy. Of those 32 bits, some bits identify the subnet and the remaining bits identify the device in that subnet. How do we know which bits? There's another address called the subnet mask, or simply an address mask or mask. This is another 32-bit value that tells us where do we split between the network portion and the host portion. Let's go through the example. Actually, we'll go through a different example than on the screen. The way that we read, the way that we use the mask is we say, for this IP address, whenever there's a 1 in the mask, the corresponding bit in the IP address is the network portion. Whenever there's a 0 in the mask, the corresponding bit is the host portion. In this example, the mask has 22 ones. That means the first 22 ones are the network portion of the address, and the remaining 10 digits are the host portion of the address. So in practice, every device's IP address comes with a mask. We have 2 values, the IP address and the mask. We'll go through another example and show how it's used in a moment. First, do the conversion. What's the IP address in dotted decimal notation? One. How do you know? You take the first 8 bits, convert to decimal. The next 8 bits, convert to decimal. How do you convert binary to decimal? Use your head, use your calculator, whatever. But do it quickly. In an exam, you don't have time to spend 10 minutes converting to decimal. 130, I have the answer. 17, 41, 129. That's the IP address. mask, one 252. So we can convert the mask into dotted decimal notation as well. 255, the first 8 bits are 1 to decimal, that's 255. The next 8 bits are 1s, 255. The next 6 bits are 1s followed by 2 zeros, which will give us 252 in decimal. The last 8 bits are zeros, in decimal 0. Another way to write this mask, an even shorter way to write the mask, note that it is 22 ones followed by 10 zeros. So you can use the slash notation, slash 22. The slash notation is just another way to write the mask. It means, slash 22 means that the mask contains 22 ones followed by the remaining being zeros, 10 zeros. Slash 18 means we have 18 ones followed by 14 zeros. Because our address is 32 bits, the slash value tells us for the mask the number of ones, and of course we can work out the number of zeros. So for an IP address, we have, it's always in binary form, but sometimes we convert it to dotted decimal notation. The same with a mask, always in binary, but can be converted to dotted decimal. A mask can also be converted to this slash notation, because a mask is typically a sequence of ones followed by zeros. Slash 22 means 22 ones followed by zeros. Let's go through an example. Do the opposite for our IP address. Write down, and we'll go through the full steps, write down the binary form of the IP address, and under that write the binary form of the mask. Where the IP address is 104.209.61.169/18. Slash 18 is the mask. Means there are 18 ones followed by 14 zeros. Feel free to add your name. You can take the course. $104 in binary. 104 in binary. You could use your phone. I'm sure that has a calculator. You could look it up on Google. $96. 2101. Correct? And it's 8 bits at the start. So it's 8 bits, so we need a 0 at the start. Okay? We can convert the decimals always to an 8-bit value. And then do it for 209. 61. 1 Convert the dotted decimal notation into binary, and now do it for the mask. The mask is easy. We just have 18 ones with /18. Because of this /18, it's the shorthand notation for the mask. 18 ones, the remaining zeros, 14 zeros. We could also write it in dotted decimal notation. Yeah? I think in all the cases at least we'll deal with, in most cases you'll see the mask is always a continuous sequence of ones. So it's either 10 ones in a row followed by 22 zeros, or 11 ones followed by 21 zeros. In theory you can have different combinations, but I think stick, at least to keep things simple, you always have a continuous sequence of ones and then the remaining zeros. So you can't have any possible mask, at least in this course. If you had a different one, you could simply write it. That is, you may have 0, 1, 0, 1, and again, the bits 1 indicate the network portion and the bits 0 the host portion. But that's uncommon. Okay? So not all possible masks, or you will not see all possible values for the mask. You'll see a limited set. What's the mask tell us? That was the easy part. It tells us, for this IP address, the first 18 bits identify the subnet. And in fact, in the same way that I call this subnet subnet A, so let's write our address. Instead of A1, write the actual IP address, 104.209.61.169 /18. That's the IP address of this device. Before I called it A1 and I called this subnet A, we can also get an address for that subnet. Instead of a letter, we have a special, what we call network address. It's an address of a subnet. And the way that we can calculate it from this information is that we take the network portion and let's mark the network portion. Remember the first 18 bits, that's to here. This is the network portion of the address. That identifies our subnet in the internet. The remaining bits identify that device in that subnet. A network address, we have these same bits in the network portion. And in a network address, it's a special address. The host bits are 0. The remaining bits are 0. This is what we call a network address. Instead of calling my subnet subnet A, I will call my subnet this. And that's why I can refer to that address in routing tables and when referring to that network. And you can convert that to dotted decimal. Dotted decimal, it becomes 104.209.00. because 0, 0. And this is the same as before. So now, instead of saying A here, I write 104.209.0.0/18. So we have a network address, an address that identifies a subnet. Instead of B, we may have a network address there. A2 would have an IP address. The first 18 bits for A2 must be these 18 bits. A3 would have an IP address, and again the first 18 bits must be the same. The last 14 bits must be different. Okay? So all the devices on the same subnet have the first 18 bits the same in this case. Note that our subnet doesn't always have to be /18. It can be a different value. /20, /19, /14. So we've introduced one new type of address. It's called the network address. It's where the network portion is the same. The host portion, the remaining bits, is all zeros. The host portion was all zeros. That is network portion, host portion of the address. Network address. So note, this is a network address, an address of a specific network or subnet. It is constructed where we have the network portion, and then the host portion is all zeros.
So normally host portion is 0.
So your computer cannot have this address. This address refers to that network. It doesn't refer to a computer, a device. This network address refers to this entire cloud, this subnet. Let's say I want to say all the computers on this network, then I can use that as an identifier or a name for that network. Your computer will never have this address because it's a special reserved address to refer to the network. Your computer needs a non-zero value here. Here we have all zeros. Your computer would need to be assigned 1, 2, 3 or whatever.
Computer is
A computer in this case, A1, A2 and A3.
it's a computer.
Computers, IP devices, devices in the network. Yeah. Host or router. So each of these subnets would have a network address. All the hosts and routers attached to each subnet would have the same network portion but separate host portions. This is what we call the host portion, and this is the network portion. The network portion of the address, this is the network address for the subnet. So distinguish between a network portion and a network address. Every IP address is split into two parts, two portions, network and host portion. Where do we split? The subnet mask tells us where to split. And then we've introduced one special address. These special addresses are described on one of the slides we skipped over. A network address identifies a subnet in the internet. Any questions before we move on?
So how are we going to know how many IP devices?
On that question on the slide about how many devices, you'll answer that in your homework. Let's go through these special addresses first. Then it will be easy to answer how many devices. So these special addresses, your computer cannot have them. They are reserved for special purposes. The network address refers to a network.
So network can
The host portion of the network address will always be 0.
Yes, the host portion of the network address is always binary zeros. And a new one called the directed broadcast. I'll explain the use, but first, a directed broadcast address, similar. The network portion is the same. With a directed broadcast address, the network portion is the same, but the host portion is all ones. This is another special address. First, understand how it's constructed, and then we'll explain its use. Network portion the same as our IP address. Host portion, all binary ones. In dotted decimal, it's 104.209.63.255. It's another special address. When do we use it? What's the use of this special directed broadcast address? Broadcast means send to everyone on a network. All I did is I took the network portion of our original IP address and set the host portion to all binary ones. That's our directed broadcast address for this network. You'll do this in the exam, not a problem? Yeah, not a problem, good. You'll need to do it yourself. You will not have Google or a website to calculate for you. What does this mean, directed broadcast? It means if I want to send, let's say F1 wants to send to everyone on this subnet. What it can do is it creates one packet, one datagram, and sets the destination to the directed broadcast address, to 104.209.63.255. That is, it sets it to this 32-bit value, the destination address. Sends the datagram. It will be delivered to this router. The router will see it's a special address and sends it to everyone on the subnet. Broadcast means send to everyone. Directed broadcast means send to everyone on a specific subnet. So this one has a directed broadcast address. These other subnets would have different directed broadcast addresses. It's a special way to send to everyone on some subnet. There's another broadcast address, local broadcast. All ones. Or 255, 255, 255, 255. This is a different special address called the local broadcast address. This is similar, but what it means is you create a datagram and set this all ones address to the destination, and the datagram should be delivered to everyone on the current subnet. If this computer wants to send to everyone on this subnet, it can set the destination to the local broadcast address, all ones address. And it should be delivered to A2 and A3, or everyone on this subnet. So there are two types of broadcast. One is send to everyone on some subnet. The other is send to everyone on your subnet. There's a difference there. You could use the directed broadcast to send to everyone on your subnet. That would work. but the local broadcast has some advantages. Let's finish with the last two, and then, because we're almost out of time, then you'll be able to do your homework. Two more special addresses. All zeros. I will not write it down, but 32 zeros. 32 zeros. 0.0.0.0. This is a special startup address. You only use that when you want to send a datagram and you don't have an IP address. You set the source to this all zeros address. Only in very special cases. Normally you have an IP address and you set the source to your IP address. But if you don't have an IP address and you want to send something, you can set the source to this all ones, that is 32 binary ones address. Special of the startup source address. Last one, and I'm sure you've seen it or you've heard of it, loopback address, sometimes called simply localhost. Where can we draw it? The first 8 bits, 0 followed by 7 ones. The remaining 16 bits, no, the remaining 24 bits, whatever you like. 127 dot something, something, something. Normally you'll see dot 0.1, 001. This is send to yourself. Loopback means if you send a packet with this as the destination, you'll receive that packet. It doesn't go out of your computer, it's internal only. It's just for testing mainly. So loopback means send to yourself. So you don't use it to send to someone else. It's when the first 8 bits of this sequence, for example, in dotted decimal, 127 followed by 3 decimal values. So in summary, all of our hosts and all of the interfaces for routers have IP addresses. All devices on one subnet must have the same network portion. So all the devices on the same subnet have the same network portion, but different host portion. Okay. Different subnets must have different network portions. In the same way as our subnets had different letters, in IP addresses, the subnets must have different network portions. And there are some special addresses which we do not use to assign to computers. We just use them for special purposes. There's a network address which can be used to identify a subnet in the internet. It is constructed by the network portion followed by the host portion, where the host portion is all ones. There's a directed broadcast address. Network portion, host portion is, sorry, did I say it wrong? Network address, the host portion is all zeros. Directed broadcast, host portion is all ones in binary. Directed broadcast is used if you want to send to everyone on another subnet. There's a local broadcast, 32 ones, used if you want to send to everyone on your subnet. There's a startup source address, 32 zeros, is used when you don't have an IP address and you want to send something, you can set this as the source. And loopback address or localhost, when you want to send to yourself, just for testing. 0 followed by 7 ones, followed by 24 of any value. Typically you'll see 127.0.0.1 as a loopback address. You can try it on your laptop. Type into your address bar 127.0.0.1 into your browser. See what happens. In some people's computers, it will show a local web page. Questions? We're out of time, but just